Hello, my name is Oliver Korten from Columbia University, and today I'm going to talk about the hardest explicit construction. So throughout computer science and combinatorics, a sort of ubiquitous problem is an explicit construction type problem, where we have some non-constructive proof that an object with certain desirable properties exists. And we'd like to match this non-constructive proof with our actual efficient deterministic algorithm, which allows us to construct an example of one of those objects. So for a concrete, maybe the most famous example is the case of expander graphs, where we have an easy probabilistic argument that an n-vertex graph chosen at random is a good expander, but it took a long sequence of works to actually match this with good explicit constructions of expander graphs. So we can sort of model these explicit construction problems generically as sparse search problems. So in this context, we're given the input 1 to the n, which simply specifies the desired size or length, description length of the object. And the goal is to output some n-bit string which possesses this desirable property in time polynomial in the size of the string, so polynomial in n. So for these problems to be interesting, we should have some reason to expect that the desired objects actually exist at all. And technically speaking, this makes the problem what's called a total search problem, where for every instance, there exists a solution. And so as is known from the study of TFNP, to sort of define interesting classes with complete problems for total functions, it usually necessitates isolating some underlying combinatorial lemma, which guarantees the existence of a solution, and then defining some canonical search problem associated with that lemma. So in the case of explicit construction problems, many of the most famous ones, the sort of widely used existence proof to show that there is some nice object is the probabilistic method, which informally speaking shows that a random object possesses the desired property with high probability or just non-zero probability. So in many cases, as we'll argue, that application of the probabilistic method can actually be reframed as an encoding argument. So the argument essentially says that any n-bit string which fails to possess the desired property can be encoded using strictly less than n bits. And this in turn implies that a random n-bit string must possess the desired property with probability exceeding a half. In previous work by Kleinberg, myself, Mitropolsky, and Papadomitriou, a class was defined that sort of captures the complexity of making these encoding arguments explicit. In particular, empty is the following search problem, where we're given a circuit C, which has fewer input bits than output bits, and the goal is to find some string in the codomain of this function, which is not in its range. So something is not mapped to by any string with fewer bits. So APEPP will then just define as the class of problems polytime reducible to this canonical problem empty. So the first sort of trivial upper bounds we can put on this class are that it lies in TF sigma 2, which is just total functions that are sort of solvable in sigma 2 time, informally speaking. And to see this, the idea is just we're trying to find some string x such that for all pre-images, they do not map to this string. So it's sort of a exists for all type of description of the problem, which puts it in a sigma 2 class. And a bit more specifically, we can show that this lies in a class we'll call FZBP to the NP. So in other words, it has a zero error randomized algorithm with an NP oracle. The idea here is just that we choose a string in the codomain uniformly at random and then test using an NP oracle if it has a preimage. And since the codomain is at least twice as large as the domain, the probability that we guess a correct answer is at least a half. So the sort of first thesis of this paper is to show that this class APEPP, this problem empty, really captures the essence of many of the most important explicit construction problems that we face in computer science. So in particular, we show that for 7 well-studied interesting problems where we don't have an explicit construction, but we have a non-constructive proof that some object exists, we can reduce the explicit construction problem associated with that to this canonical problem empty, and thus place this problem in APEPP. So for example, we'll show this to hold for truth tables of high circuit complexity, constructing those, constructing good pseudorandom generators, randomness extractors, rigid matrices, and several other interesting objects. So to sort of give you an idea of how these reductions work, we're going to start with the case of hard truth tables. So a truth table is just an explicit representation of a function on n bits to 1 bit. And we represent it explicitly by writing out its values on all of the 2 to the n and bit strings in order. So it's some 2 to the n bit string. And the idea is we want to construct a truth table which requires large circuits to compute in time polynomial in the size of the truth table. So big N is what we'll call when little n is the number of variables. And so a simple argument originally due to Shannon says that we can specify a circuit of size S using approximately 2 S log S gates. This is a very simple encoding where we just say for every gate what are its 2 inputs and what logical type it has. And this can easily be used to show that basically if we let big N be the size of the truth table, any truth table computable by a circuit of size big N over 2 log big N can be represented using big N minus 1 bits. So strictly less than an arbitrary truth table of length big N. So this immediately implies a reduction to the problem empty in the following way. We construct an instance of empty, which takes big N minus 1 bits, interprets it as a description of a circuit of size big N over 2 log big N, evaluates it on all little n bit strings. So there's big N of those. So we evaluate that circuit on every possible input and then just print out its truth table, which we get as a result of this. And that truth table has length big N bits. So this is a valid instance of empty because we have fewer inputs than outputs. And every string which is outside the range of this map must be a high circuit complexity truth table. So if we can solve this problem of empty, we have got our hands on a particular truth table of high circuit complexity. So the hard truth table construction problem reduces to the problem empty. So for a second example of this, we're going to be a bit more informal here, but we're going to show that the construction of pseudorandom generators in the sense of Nissan-Wigderson can also be reduced very easily to this problem. So a pseudorandom generator, again, informally, is a sequence of n-bit strings, S1 through Sm, such that if we feed a circuit C of size n, a uniformly random string from this set S, the probability that C accepts is approximately equal to the probability C accepts a truly uniformly random n-bit string. We're going to be a bit vague about what approximately equal here means, but just it's some bound that depends, let's say, polynomially on n, on big N. Sorry, so 2 to the n. So to reduce this to empty, we're going to fix the size of this pseudorandom generator, the number of strings in it, to be about n to the 10, just some large polynomial n. And the idea is let's just consider an arbitrary sequence of strings, S1 through Sn to the 10, each an n-bit string. So by Yao's next bit predictor lemma, which we won't cover here, but it's a relatively standard, straightforward probabilistic argument. If this set S fails to be a good pseudorandom generator, then there is some bit I in amongst the n possible bits in a circuit D, which we'll call the predictor circuit of size O of n, such that D can predict the ith bit of Sj from the remaining bits for a significant majority of the strings Sj in this supposed pseudorandom generator. So this is going to immediately give us a compressed representation of S whenever S fails to be a good pseudorandom generator. And the idea of this compressed representation is we just eliminate the ith bit of every string in S. And overall, this is going to save us n to the 10 bits because there are n to the 10 strings in S. And then from there, we're also going to need to add a couple more bits in this encoding because we're going to need to specify the predictor circuit D. But this is only going to cost about O of n, really O of n log n bits. And also, we're going to need to specify the ith bit of Sj for the small number of Sj that our predictor circuit failed to predict on. But Yao's next bit predictor lemma gives us a good enough bound that there's a small enough number of those failures on the predictor circuit that we can still save on the total number of bits by sort of encoding this small number of failures. So overall, when S fails to be a good pseudorandom generator, this gives us a natural compressed representation from which we can recover S. And this immediately implies a reduction to empty, where the instance of empty just maps that compressed representation to the original S. And any true good pseudorandom generator cannot be in the range of that. So constructing a good pseudorandom generator reduces to empty. So at this point, hopefully I've given you somewhat of an argument that APEPP is an interesting class insofar as it captures a lot of interesting explicit construction problems. Sort of the next measure that we want from a complexity class is that it also contains an interesting complete problem. And so although empty contains trivially the complete problem, sorry, APEPP trivially has the complete problem empty, this is maybe not so desirable because empty is not an explicit construction problem. It does not have a sparse input. So our sort of motivation is we want to find an explicit construction problem, hopefully a natural one, which is actually complete for this class. And so our next result is going to be that actually the construction of hard truth tables is complete for this class APEPP under a sort of weaker notion of reduction where we get to use an NP oracle. But if you recall, the only natural upper bound on this class is sigma 2. So NP oracle reductions are still going to be non-trivial in this context. So sort of the core of this theorem actually dates back about 20 years ago, where Emil Jerzebek showed a very sort of equivalent of this result in bounded arithmetic, where he showed that a certain theorem asserting the empty pigeonhole principle is equivalent in this fragment of bounded arithmetic to the theorem asserting the existence of hard truth tables. And so what our result is going to do is we're going to sort of translate this into an algorithmic statement, which gives a reduction from empty to the construction of hard truth tables using an NP oracle. So to define the construction problem we care about explicitly, it's going to be we're given 1 to the n, and we want to find a length n truth table that requires circuits of size n to the epsilon. We're going to call that problem epsilon hard, where we fix epsilon to be some constant between 0 and 1, an arbitrary constant. To start out this reduction, right, we have some instance of empty, and we're going to assume that this instance has twice as many outputs as inputs. So it has n inputs to n outputs. We show in the paper this is without loss of generality. So the idea, the sort of first step here, is that we're going to iterate this function c into a tree of depth k. So the way that we do this, for some parameter k, we're going to start with feeding n bits into c. That gives us 2 n bits. Then each of those n bit blocks can be fed again into another copy of c. And we can do this k times. And this iterated function we'll call c star is going to have n inputs and 2 to the k times n outputs, where k is some parameter that we're going to choose in a moment. So sort of the first important property of this construction is I claim that any string in the range of c star is necessarily going to have somewhat low circuit complexity if we view it as a truth table. So the argument here in particular is that there's going to be a circuit of size about the size of c times k for any string in the range of this map. The argument here is we go back to the last slide. We imagine just writing the bits of a particular string in the range of this up at the top of this diagram. Then I claim that given a certain preimage, an n-bit preimage, using that as advice, we have a very efficient algorithm running in c times k time to compute a particular bit of that string in the range. And the idea is that given a particular leaf that a bit lies at, we can use k bits to specify whether to go left or right at each step of this path. And then given that, we just compute c on the preimage k times going left or right, depending on the sort of index of the leaf that we're going to. And this just gives a diagram of what that specific circuit looks like. We fix the preimage x as advice, and then use this left or right decision to evaluate the circuit c k times. So my next claim then is that we can set the parameter k so that things work out nicely. In particular, there's a value we can set it to so that it's logarithmic in the size of c, so that if we write out this entire tree, it's still a polynomial time reduction. And second of all, we can get it so that any string in the range of c is necessarily not a solution to epsilon hard. In particular, its circuit complexity will be 2 to the k times n, which is the length of the truth table, raised to the epsilon. So at this point, we're very close to finishing the reduction. What we have done is we've established that from any c, we can construct c star so that any solution to epsilon hard is necessarily outside the range of c star. The next step now is just to show that given a string outside the range of c star, we can use it to find something outside the range of c, which is our original problem empty. So the idea here, again, is pretty simple. We look back at this tree, which computes c star, and we imagine we have some string which is outside the range of this whole thing, and we write down the bits of it at the top of this diagram. Now what we're going to do is for each 2n-bit block, we try to invert it under this map C using our NP oracles. We try to find a preimage. If we can do that for all possible blocks, then we get to the next layer, and then we try to do that again. And we do that for all layers of the tree. If we're able to invert all the way to the input, then that means the string must have been in the range of C star. So if we assume that it's not, then at some point, one of these preimage calls fails. in which case we found a 2n-bit string outside the range of C, and that was our original goal. So that completes the entire reduction. And we have that given a solution to epsilon hard of a sufficiently large length polynomial in the size of our instance of empty, we can solve the problem empty using an NP oracle. So this result is especially nice because the existence of a p to the np algorithm for epsilon hard is equivalent to the existence of a language in e to the np of circuit complexity 2 to the omega n. This is really just a simple argument, like basically using padding and rephrasing things. And so what we've really shown is that this problem empty, a natural sort of search problem, has a p to the np algorithm if and only if a certain circuit lower bound holds, a certain exponential circuit lower bound. And in other words, this also shows us that proving this circuit lower bound for e to the np, which is a well-known open problem, is sort of equivalent to a generic de-randomization of the probabilistic method of construction. In particular, it would imply pretty explicit constructions, like NP oracle explicit constructions, for this variety of problems that we showed lie in APEPP. So in particular, I sketched earlier to you a proof that construction of pseudorandom generators reduces to empty. And so pairing this with the completeness result, we have a very simple new proof of the hardness randomness connection of Impaliazzo-Vigerson and Nissan. So in particular, right, this result shows that if we can construct a table of high truth complexity, we can use that to worst case complexity. We can use that to de-randomize an algorithm by constructing a pseudorandom generator. So this is sort of weaker than Impaliazzo-Vigerson in the sense that they don't need the NP oracle, but the proof is very significantly simpler. In particular, I just sort of sketched the whole thing to you in about 10 minutes. So that's sort of one interesting application, but it doesn't actually get us a new result because we have the stronger version by Impaliazzo-Vigerson. But a truly new result that we do get from this in circuit complexity is what I'll call a worst case to worst case hardness amplification theorem. So in particular, the theorem says that e to the np contains a language of circuit complexity 2 to the omega n, if and only if it contains a language of circuit complexity 2 to the n over 2n. And the argument here is basically we have all the tools already available to us. At the very first proof I showed you, we saw that construction of a truth table of like 2 to the n and hardness 2 to the n over 2n, so like the very high end hardness, already reduces to empty. And then in turn, I showed you that empty reduces to the problem epsilon hard for any fixed epsilon between 0 and 1. So this says that if we can construct these weakly hard truth tables, then we can also construct these very, very hard ones in the regime of NP oracle computations. So translating this to like languages and circuit complexity, this gives the stated result. So finally, sort of a natural thing to think about this is that this result sort of seems like it's giving a hardness randomness connection. In particular, I told you at the beginning of things that this problem empty has a natural randomized NP oracle algorithm where we just randomly sample a string and test if it has a preimage. And so this result is really saying that we can de-randomize that algorithm if and only if e to the np has high circuit complexity. And so naturally, we'd want to compare that to sort of previous known hardness randomness connections based on the Nissan-Vigerson and Impaliazzo-Vigerson generator. And so in particular, those old set of results, they are known to extend to NP oracles, different oracles. And what they would tell us is that if e to the np requires non-deterministic circuits of exponential size, then APEPP has an FP to the np algorithm. So basically, previous results require a hardness for a much stronger model of circuits, non-deterministic circuits. And in particular, that old result does not give us an equivalence because it's not known that hard truth tables for non-deterministic circuits reduce to APEPP. So our new result shows a de-randomization under a strictly weaker assumption. And in turn, we get an actual exact equivalence between de-randomizing this algorithm for empty and proving a certain circuit lower bound for e to the np. So that's the end of my talk, and thank you for attending.